questions. All right, guys. So we've talked about the rhombus last week. And the rhombus is basically just, we got a four-sided figure that is a type of parallelogram. The opposite sides are parallel to each other, but we have four equal sides. And so the part about this that I did want to make sure, it was interesting because I was at home. Oh God, I don't even know when it was earlier in the week, like maybe Monday. And my son and stepson were at the breakfast table talking about the difference between a square and a diamond. I'm like, man, this is topical. This is something I actually get to teach this week. And so they were going back and forth, and like they basically said, I think I've got, so let's say this is a square because this is like a calendar page thing, right? I said, well, the difference is you just take it from this and you just turn it on its side. And I'm like, that's not exactly right, because this is like a square, right? We got four equal sides and we've also got right angles. So yes, this is kind of a diamond because it's off on the side and we're looking at a rhombus. But at the same time, really what we're thinking about is the idea that if I push those corners in, these angles themselves don't all have to be 90 for all four sides to be equal. So that if I sort of take B and D here and push them towards each other, these angles C and A get smaller and these angles B and D get larger. The interior sum is still going to be 360 because it's still a quadrilateral, and it's still something where I know, because this is a parallelogram, that B and D will be congruent to each other and A and C will be congruent to each other. But understand, rhombus just has four equal sides, and that's kind of the way we're going. Now, with that being said, we know that it's got four congruent sides. We know it's not always a square. And you know what? I'm going to say this perfectly, because Malin, you said this the right way privately, but I'm going to say it out loud because it's great. A square could be a rhombus, but not all rhombuses are squares. It's a really good way of us doing this classification. Now, stuff you need to know about these guys. If a quadrilateral is a rhombus, then it's a parallelogram. So these are all parallelograms. It's not too hard to kind of recognize that we're doing this. We could prove this, and I could go about proving this by sort of dealing with having the sides that are here. It's not hard. Guess what? Opposite sides are congruent. If opposite sides are congruent, we know it's a parallelogram. So guess what? Ha! There we go. Here's the other thing I want us to do. So if a parallelogram is a rhombus, then we know diagonals are perpendicular, so that I know that right on the inside here, these angles are all going to be 90. Now, this is a new one, and this is one you got to kind of dig into a little bit, okay? And so we're going to talk a little bit about how this gets proven when we go through this. But I do just want to make sure that, if for no other reason, you guys have this sort of as a piece that goes into your memory. This is a really, really easy way for us to incorporate the Pythagorean theorem into problems that have to deal with parallelograms, and in this case, rhombuses in particular. So, or rhombi in particular. Because if I know that these are all 90-degree angles, now I got four right triangles on the inside of this. And these four right triangles in here, I could give you two sides and you'd have to find this. And I'd say, if I know this length and this length, what's the perimeter of the outside here? And you'd have to recognize, oh, wait, I'll have to use the Pythagorean theorem to find AB. And then there's four of those, so I'll have to multiply it by four. It's a really easy way to sort of incorporate this type of math that we've already done. But it's also interesting that these are perpendicular. Now, I think that I did the proof outline. I did. So here's what we're going to do. You guys ready to be baffled by our proof outline? And I believe that I'm using this specific rhombus for what we're going to be looking at. So if it's a parallelogram, which we know they already are, the diagonals bisect. So we know that AX and CX are congruent to each other. Everybody all right so far? You got to say yes. Like right now, if there's not a response, I got a Y. That's good. There's another Y. There we go. Thanks, guys. Thank you for participating. It makes me happy. Okay, so far, we know AX and CX are congruent to each other. I think I'm going to mark these as I go, mostly just because I think it's easier for me to kind of do that. But I want to do this with a different color because I think it's going to be harder to see if I use that. So let me use green. All right, so that means that this and this are congruent to each other. Okay, next, maybe. It's a rhombus. We know that. So we know that AB is equal to CB. Now it's already marked. And really, I should have marked these with 2. I'll probably go back and do that just so we're kind of in the same page. Because when I look at this one, I know that these are congruent, but they're not congruent to the outsides. So that's fine. right, so right now we got this is congruent to this is congruent to this. Do you guys see the other part of this we're about to use for dealing with congruent triangles before I actually say it? Anybody see this one right now? Oh, come on, y'all. Oh, think about this. If I'm proving that this triangle on the left, ABX, is congruent to this triangle on the right, CBX. I see somebody asking BX is congruent to DX. You are really close. You used half of it. I'm only talking about this triangle and this triangle. They got the shared side in the middle here. So I can say that this left-hand side and this right-hand side triangles are congruent. Now, it's also true that they're congruent to DX. I can, in fact, prove that all 4 of these triangles inside here are congruent to each other, but it's the shared side that I'm looking at in the middle there. At least that's what I would do right now. I actually made this slide presentation like 2 weeks ago, so my brain has not quite stored what I had done in there. So I think I say shared side. Yeah, look at that. Shared side, ABX is congruent to CBX. So we've got those 2 triangles congruent to each other. Now, here's why that's helpful. Because what I need to start to think about is this. I know that as I'm looking at this, that I am going to be looking at these angles on the inside here, and I want to make them 90. So I know that this angle AB, AXB, and CXB are congruent to each other by CPCTC. So 2 congruent angles. But if I look at them, they're also a linear pair because BX is a shared side of AXB and CXB, and they make this whole line here AC. So congruent angles on a linear pair means that both angles have to be equal to what? Linear pair adds up to 180. These 2 guys are congruent to each other. What do they both have to be? Yeah, they got to be 90. Because if they're both 180, if they add up to 180 and they're equal to each other, you take that 180 divided by 2, you got them both as 90. So I know by the definition of being perpendicular that this has to be perpendicular to this. Now it continues all the way through, and I'm showing in this case then, based upon the fact that I've got 2 congruent angles in a linear pair, that this line BD has to be perpendicular to this line AC because it creates 2 right angles, but 2 right angles also mean 4 right angles when we look on the outside here. All right, that is our outline of a proof. Sometimes these are easier to just kind of talk through, and that's sort of what I wanted to make sure that we were able to talk about, but that is what we're looking at there. So everybody cool with that general idea as to why they would be perpendicular to each other? All right, awesome. Moving on up, I think. All right, here's the other thing. And we can use the same congruent angles, congruent triangle things. It's essentially that when I have these, I know that these are perpendicular, but I also know that each time I have a diagonal rolling through here, it bisects a pair of opposite angles. So angle B and angle D here are congruent to each other. And when this line slices through here, 1 and 2 are congruent, and 6 and 5 are congruent to each other. So right now, all 4 of these angles are equal to each other, and it's bisected. And then in this case, yeah, so you could say 2 is 6, 1 is 5. We can totally say that. But the fact that they're equal to each other is because we just proved very quickly that this angle, this triangle here, AB would have been X, and CBX are both congruent to each other. All 4 of these triangles are congruent. So this angle corresponds here, here, and here. This angle corresponds here, here, and here. So we are going to be looking at angles that are congruent to each other. Is 2 congruent to 5? Absolutely yes. 2 has to be equal to 5 because 2 and 1 are equal, 2 is equal to 6, 6 and 5 are equal, so 2 has to be with 5. They're also all CPCTC, a part of the same triangles that are made here. Any other questions about things being equal here? Anything that's in blue is equal, anything that's in red is an equal. Anybody else with questions about this? I can't remember if I did an outline of this proof or not. And if I did, I'm going to kind of rip through it for time. Nope, I didn't. All right, this is where we start to get into what the problems actually look like. So here, all right, let me look at my time here. We are looking at, I can't see the time up on the top. Let me pull out my phone so I can actually see the actual time. 10:57. Okay, so we got about 7 minutes left in class. Thank you, I appreciate that. So looking at this, it's a rhombus. What can I do to find X in this case? I think we can do this one pretty quickly. I'll do this through annotation. Yep. Somebody wrote it privately. Caroline, you wrote it privately, but you wrote it right. I can say that these two things are equal to each other because all four sides of a rhombus are equal. So I know that 9x minus 11 is equal to 4x plus 7. And then I can take 4x from both sides and get that 5x minus 11 is equal to 7. Then I can add 11 to both sides, and I can say that 5x is equal to 18. And then I can divide everything by 5 and say that x is equal to 18 over 5. Let me tell you, that is an ugly, terrible, awful answer that is also mathematically correct. Everybody good? Now, did I do my math right? Looking. Yeah, I don't think I did anything wrong
But
there.
if you said the answer is correct, then it has to be done right.
I know, but I'm making sure because I didn't check to see if those answers are right. That's everything that I just did seems right, but 18 over 5 would absolutely be correct. All right, cool. So you guys good? That makes sense? Somebody has to say something. Yes? All right, cool. So let us move on. Because I do want to get to the next piece that we're going to be talking about. I think there's another rhombus problem here. Let me see. With this one, what you would have to do, this is actually kind of an interesting piece of work here. What would you do here to find out what y is equal to? If I know this is a rhombus, what would you do first? What would your equation be to be set up? And this is written privately, but that's absolutely right. I know that because these are perpendicular. I don't know enough about this one yet. So I don't know that these two would be equal to each other, but because I know that these are perpendicular, I can say that 2y plus 10 has to equal 90 because it's one of the angles on the inside here. Once I know that, I could plug in that y value into this top one to find out what this top angle is. So really quickly, I could go about doing that, and I'm just so the setup would be that 2y plus 10 is equal to 90. If I subtract 10, I get that 2y is equal to 80. And if I divide by 2, I get that y is equal to 40. So that means that this guy up here is going to be 42. And actually, so V, you just said you thought they were sides. You always want to look at what's being pointed to. And they are written in such a way that they do look like sides. Look for those little lines pointing to what it is that's there. And these little indicator of the degree mark is the other part that's to sort of let you know, wait, this is a little bit different. So once we know what y is, we can plug that in. And I know stray scribbles is definitely something that you can see. It's just something to pay attention a little bit because that is the way that a lot of math books will do it. And I just kind of want you guys to have your heads around that a bit. Okay, next one. Am I doing another rhombus problem? Oh my God, no, this is the one that I feel kind of bad about. We're gonna talk about the square. I totally forgot about this. So
That's
rectangles
actually amazing.
cheating on trapezoid with rhombus. I totally made this. By the way, I sincerely do not suggest that you try to find this movie because I typed in Love Child into the image source. You really don't want to do that. This one has mature themes, violence, sex scenes, and nudity. I don't really know how that would apply to shapes, but it was kind of fun to be able to say, hey, look, it's a love child between the rectangle and the rhombus. They made a square, or in this case, two squares. Anyways, yeah. And I'm recording this, so that's going to be played back for all time. Yay. Okay. The love child is the square.
Forever.
I feel great about this. Just to make sure that you do recognize, there's not a whole lot you're going to be doing with the square. But if they do give you a square, just recognize this is something that every rule that applies to the rectangle and every rule that applies to the rhombus, all of those work with the square. Okay. And so as we start talking about this, if they give you a square to work with, just realize we've got 4 equal angles, we've got 4 equal sides. I know that the diagonals are going to be perpendicular, but I also know the diagonals are going to be equal to each other because that's what it is in a rectangle. I know that each of the diagonals is going to bisect a pair of equal sides. So everything here is going to be 45. So just be on top of that. Okay. I just want to make sure. Yes, Mr. Mitchell does use these. I gave him a heads up about this, and apparently he did not speak about the love child. And now I have that song in my head, Never Meant to Be. The square child, never meant to be. Okay. Hey, look, guys, homework, yo. And a dope picture of a cat. I actually typed in dope picture of a cat to find out what would happen. And this, my friends, is what we looked at. This is a pretty cool looking cat. I also want to let you know what's going to be coming up in the next section of things that we're going to be going through tomorrow is another set of quadrilaterals that are going to have a whole new set of rules. But this was sort of the end of our special parallelograms. And so we're going to be moving from parallelograms to other things tomorrow. But for this, you've basically got two problems that you have to do, problem 23 and 42. One of them is a rectangle, one of them is a rhombus, but these are good practice problems to kind of go through and see that you understand what's happening here. So this is already up on Google Classroom. This is something that I would like for you guys to kind of give a chance to try. And what I'll try to do tomorrow at the beginning is to go through and maybe go through, somebody had asked about question 6 on the earlier assignment, and I maybe be able to go through this one for 6.2 on the question as well. Which sides the expressions are representing. I'll tell you what, I will do my very best. Let's take a look at something like this and see what it is that we can do. All right. If so, the person that asked me privately about what sides the expressions are representing, take a look at it, see what we can do with this, and then we'll talk a little bit about it tomorrow because I am a little bit out of time. So let me stop recording